the T-Tauri phase of star formation. Now, after the star had been a protostar, it is now in the T-Tauri phase. It has in the center 5 million degrees, but it has at the surface just 4,000. It is still not hot enough for the thermonuclear reaction with making in the inside of the pressure all the hydrogen atoms together to form helium. It's not hot enough for that. But the gravitational contraction continues, that's all. But now the point is, it has already 4,000 degrees at the outside, so it got hotter and hotter during the protostar phase, with kinetic energy more and more pressing together through the gravitational contraction just by itself, basically. Now, in these 4,000 degrees also at the surface lead for the gases in all it to become ionized, to become ions, to become basically plasma. Now, it happens like that. Gas is normalerweise neutral. And now it happens that they are shaken apart through the heat, and my interpretation is that these atoms have in the center the protons with the same number as electrons on the shells on the outside. Now, if it gets too warm, the valence electrons, the electrons one electron at the outside, is shaken apart because it's so hot. It loses that one electron. It's just too hot and it bursts, basically. It falls apart and it loses one electron. And through that, every atom has the same amount of protons in the center as electrons and is therefore neutral. But now it has lost an electron. It has now one proton more than electrons, and it is now positively charged. It is no longer neutral. So this process is an ionization, and all these atoms, because it's 4,000 degrees hot, all these gases are suddenly no longer neutral, but electrically charged. Now, the T-Tauri star, in its formation, is bigger than the Sun, and it's also rotating faster. And all these electrically charged particles, or gases, are now rotating, and a rotating electrically charged thing is an electrical current, basically. The thing is basically an electric current, and every electric current has a magnetic field. And this magnetic field now goes through the space. Around it, it has also a global magnetic field. It goes then also around the space through the protoplanetary disk and sucks out all the gases with its magnetic field. And at that point where they hit then the T-Tauri star, there's now a violent reaction. And that is one of the hallmarks of a T-Tauri star phase of a star. And they're also bursting out of flares out of these T-Tauris. That's also happening. And that is according to Mark A. Garlick's Cosmic Manigalee book on the page 37. Hi and welcome. I am trying to learn Heliology. Today, T-Tauri stars, and after we've done that, we're gonna do hip training. And if you participate in the hip training, I said that your arms. T-Tauri stars. A star's T-Tauri phase is violent. The star is still undergoing gravitational contraction, but is not yet hot enough to drive thermonuclear reactions. So gravitational contraction of the giant molecular cloud, which was all the dust which had pulled together, is still happening for the protostar phase, or the pre-protostar phase. And now it's a T-Tauri phase that is still happening. But it is not hot enough yet. 5 million degrees in the core temperature at the protostar phase at the end, after being for 100,000 years, no, 1 million years. 1 million years later. 1 million years later, it reached 5 million degrees, and that is still not hot enough to drive thermonuclear reactions. However, with sufficiently hot surface temperatures of around 4 million degrees Celsius, so it is 5 million in the center, but 4,000 just at the surface. And at that point, virtually all its gases are electrically charged. So the gases are electrically charged. In a gas, atoms are usually electrically neutral because they are made up of equal quantities of positive and negative charges. Gases are usually, the atoms of a gas are usually electrically neutral because there are the same amount of positive as negative charged atoms in it. But if a gas is hot enough, the heat shakes the atoms apart. This is known as ionization. And the charged atomic fragments are called ions. I think I know what we're doing. We did recently in biochemistry ionic bonds. And that was said in an ionic bond to form ions, one atom is gaining or losing an electron, and it is the electron sitting on the outside of the valence shell. So there's the atom with the protons and neutrons and the atomic nuclei, and then the electrons on the valence shells, on the outer shells, and then the valence shell, the outermost one. And by ionic bonds in biochemistry to form ions, where this electron on the outermost shell is lost, or if it has already 7 on the outermost shell, with 8 it is full and happy, it can get an 8 one. What we're telling here is the heat shakes the atoms apart. But I understand here, and that is called ionization. But I understand here, it gets so hot that the one valence electron at the outside is lost, like a high-speed car or a train or whatever, where something gets lost because it's driving so fast. And that electron is lost, and now it has 1 electron too little. It's had lost an electron. Every atom has the same amount of protons in the center as electron on the outside of the shells. Now it has lost an electron, so it has too little electrons, or it has too much protons. And protons are positive. And now our atom is a positively charged one, and no longer neutral. That is called ionization, and they are now ions. So a T-Tauri star, like a true star, is a gigantic ball of electrically charged gas. It's called a plasma. And that thing is now a plasma. So the whole gas is now electrically charged, gas or a plasma. Compared to a star like the Sun, the average T-Tauri is typically a few times larger and spins more quickly on its axis. Once in a few days, the Sun takes a month. So a T-Tauri star is larger than the Sun and spinning faster. The Sun spins once a month. And it is larger and spins faster, a T-Tauri star, with its electrically charged ionizations, ions, plasma. Not hot enough for thermonuclear reactions. Since a moving charge constitutes an electric current, the star's interior is full of electricity. Just as a wire carrying an electric current generates its own magnetic field, the circulating ions inside a star create a global magnetic field. That thing is circular, and because it is electrically charged, it is an electrical current which is running. And every electrical current has a magnetic field, everyone. And this magnetic field is doing things. In the case of a T-Tauri star, the rapid rotating creates a much stronger magnetic field than in more normal stars. So because it's rapidly rotating, the electrically charged particles are rotating faster, and therefore the carrying electrically charged is faster, and therefore the electromagnetic field is bigger. Furthermore, a T-Tauri star is usually surrounded by the protoplanetary disk that built up around it as it grew. Around it is the protoplanetary disk, whatever that means really. As the star rotates, its magnetic field lines are dragged through this disk. Where the field and disk interact, streams of gas are sucked out on the disk, the protoplanetary disk. The gas are sucked out of the disk and pulled along the field lines onto the star's surface. Where these packets of gas hit, the stars respond with violent magnetic flares, a hallmark of a T-Tauri phase of star formation. And there are no violent magnetic flares. And that is the hallmark of a T-Tauri star's phase, of a star's which is in a T-Tauri phase. A final characteristic of a T-Tauri star is a powerful stellar wind, a stream of ions that blasts us away from the star deep into space. The Sun has a similar wind, but it is much slower and more rarefied than the one in its T-Tauri Atlas sets. So powerful stellar wind, which is a stream of ions that blasts us away from the star deep into space. And also that. Okay, do I know all the information? I think I do. I'm going to start with the camera. Let's look how we come and if you have to reorganize the presentation. The Tauri formation, Tauri phase. The Tauri phase of star formation. Now, after the star had been a protostar, it is now in the Tauri phase. It has in the center 5 million degrees, but it has at the surface just 4,000. It is still not hot enough for the thermonuclear reaction with making in the inside with the pressure of all the hydrogen atoms together to form helium. It's not hot enough of it. But the gravitational contraction continues, that's all. But now the point is, it has already 4,000 degrees at the outside, so it got hotter and hotter during the protostar phase, with kinetic energy more and more pressing together through the gravitational contraction just by itself, basically. Now, in these 4,000 degrees also at the surface lead for the gases and all it to become ionized, to become ions, to become basically plasma. Now, in heavens like that, gas is normalerweise neutral. And now it happens that they are shaken apart through the heat. And my interpretation is that these atoms have in the center the protons with the same number as electrons on the shells on the outside. Now, if it gets too warm, the valence electrons, the electrons one electron at the outside, is shaken apart because it's so hot. It loses that one electron. It's just too hot and it bursts, basically. It falls apart and it loses one electron. And through that, every atom has the same amount of protons in the center as electrons, and is therefore neutral. But now it has lost an electron. It has now one proton more than electrons, and it is now positively charged. It is no longer neutral. So this process is an ionization, and all these atoms, because it's 4,000 degrees hot, all these gases are suddenly no longer neutral, but electrically charged. Now, the Tauri star, in its formation, is bigger than the Sun, and it's also rotating faster. And all these electrically charged particles, or gases, are now rotating, and a rotating electrically charged thing is an electrical current, basically. The thing is basically an electric current, and every electric current has a magnetic field. And this magnetic field now goes through the space. Around it, it has also a global magnetic field. It goes then also around through the space, through the protoplanetary disk, and sucks out all the gases with its magnetic field. And at that point where they hit when the Tauri star, there's now a violent reaction. And that is one of the hallmarks of the Tauri star phase of a star. And they're also bursting out of flares out of these Tauris also. That's also happening. And that is according to Mark A. Garlick's Cosmic Manigalee book on the page 37. I'm going to stop the camera. I'm not sure if it was maybe a little too fast, the thing with the losing of the electron part. But I think we have a good video, and we're going to continue. And in the next part with the main sequence of the Sun. That means if you're here for helioscience, you can go directly to the next part of helioscience, or to biochemistry, or to electrical engineering, which you have also, and probably at some time also physics. We have physics. You can go there, or you go to Heliology, where we continue with Sun's phase, the main Sun phase. If you stay here and participate in the Hiptraining, then it's very honest. And we're having the feet sending together. Toes are going to the outside, the other toes. The heels and the heels, toes, toes, heels, heels, toes, toes, and a bit on. And again in. But this time stay down with the knees, or with the head, so that you go into the knees a bit. And come again in. And up. Hip width apart, a bit further apart, into the knees, and now flex the legs and press them together, and straighten one leg slowly. Press together, flex the whole time. And other leg straighten it, press together, flex, and bend it again. Further apart, bit down into the knees, flex, press together, go over to one side, so that the legs get straight. Back into the middle, to the other side, straighten the leg, and back into the middle. Up again, a bit closer together, and press to the outside. One leg up to the outside, breathe in, out into the middle, and down. Other leg up, out, breathe in and down. And now, one leg to the side of the toes and lift it up and make a flexed foot at the top. Try to be stable with the hip, so just the legs moving. And on the other side. And now, one exercise. Leg up and press up and to the side. Our leg up and to the side. One hand on tummy, one on lower back, and lift the leg up in a straight line. Try to bring the leg higher. Control the hands that you don't fall back. And bring the leg up. Upper leg. Pull the toes in and try to bring the leg higher. And up. And the next exercise. Stand good on one leg. Turn slowly over. This can go to the knee. Down. Again over. Slowly control it. Up. Upper side. Stand good. Turn over. Again down. Slowly over. And up. Next exercise is X. Don't do it if you're pregnant. Heel onto the ground. Lift the heel off the ground and place it again onto the ground. Other side. And toes pointing to the outside. Ulnar length space between the heels. Breathe in the outside. Breathe out, sink down. And when the hands onto the ground, the back up and the shoulders, slowly with the shoulder back up again. And the top of the backwards shoulder. The illusionistic down sitter exercise. Again, in and up. Out and down. Hands onto the ground. Back up the shoulders. And the seesaw airplane, leg back, up to the side, and the leg up. And again, back and back in the middle. And hiding airplane, leg in and out. And the other leg, arms to the side, and leg back, middle, and again back, and now pull the leg in, a hiding airplane, and down. Legs to the side, breathing out. And outside. And out. Breathe in and close the legs. And breathing out. That was the hip training. I thank you very much. And